Navigating the sheer volume of health information out there today can feel less like drinking from a fire hose and more like, well, being swept away in a tsunami of data. Seriously, you start looking for ways to manage something as common as blood lipids. Maybe
Hmm.
you've heard terms like cholesterol or triglycerides, and suddenly you're just buried under stacks of research papers, dietary guidelines, and honestly, a lot of conflicting advice.
Oh, absolutely. That overwhelming feeling is completely real.
Hmm.
The landscape of health information, especially when you look at conditions like hyperlipidemia, which is, essentially having elevated levels of fats in your blood,
Yeah.
it's incredibly dense.
It really is. And often the conversation you hear in the mainstream, it kind of starts and stops with basic diet adjustments or maybe discussing conventional medication.
Exactly. That's often the boundary.
But our sources for this deep dive, they really push beyond that. They explore what feels like the frontier of research, these cutting edge studies investigating natural compounds, herbs, plant extracts, stuff that's showing some really fascinating potential.
Hmm.
So, our mission today really is to take this stack of source material, and it's quite varied, ranging from detailed research papers to broader reviews, and really extract the most important nuggets of knowledge and insight. We're focusing specifically on some of the, well, extraordinary findings observed in rat and human subjects.
And you're absolutely right. We're deliberately going to zero in on some of these potentially remarkable results from these specific studies. Some of them might even seem a bit outside of the realm of the commonly known herbal remedies you might already be familiar with. We really want to show you what the scientific community is actively exploring in these perhaps newer areas.
Yeah, get beyond the usual suspects for a bit. We've got a really diverse collection of sources here, covering just a wide array of natural substances and study types. So we're going to unpack the evidence that's presented, analyze what these studies actually found, and then, discuss what it might imply. But always maintaining an impartial perspective, just looking at the results as they are presented in the material.
Think of us as your guides through this research, basically highlighting what stands out.
Exactly.
And maybe before we dive into those specific compounds, to truly appreciate what they're aiming to influence, let's briefly set the stage. Let's define the challenge itself, hyperlipidemia, based on the sources you provided.
Okay, sounds good. Let's unpack this challenge then. Hyperlipidemia. What exactly does that term mean, drawing from our source materials?
So according to the sources, hyperlipidemia is defined as a medical state. It's characterized by an increase in the concentration of one or more of the plasma lipids in the blood.
Okay, plasma lipids.
Right. This list includes things like triglycerides, cholesterol itself, cholesterol esters, phospholipids, and also certain key plasma lipoproteins. The sources specifically call out very low-density lipoprotein, or VLDL, and low-density lipoprotein, which most people know as LDL.
The bad one, right?
That's the one often labeled as bad cholesterol. Yeah. And often this condition, hyperlipidemia, it also involves having reduced levels of high-density lipoprotein, or HDL, the so-called good cholesterol. So in essence, it's really an imbalance. Too much of certain fats and fat-carrying particles floating around in the blood, often coupled with too little of the beneficial ones.
Got it. So it's not just about your total cholesterol number. It's really about the specific types of lipids and lipoproteins and their balance. And why is having these elevated plasma lipid levels such a significant health concern? What do the sources say?
Well, it's a major concern because, as the sources consistently emphasize, this elevation is identified as a leading risk factor for cardiovascular diseases, or CVD.
Yeah.
And we're talking about a whole spectrum of serious conditions here. Things like atherosclerosis, that's the hardening and narrowing of arteries because plaque builds up.
Right, the plaque buildup?
Exactly.
Yeah.
Also, coronary artery disease, or CAD, angina, which is that chest pain caused by reduced blood flow to the heart muscle, ischemic heart disease, and of course, myocardial infarction, which is the clinical term for a heart attack.
That direct connection between high lipids and these really severe heart conditions, it makes understanding hyperlipidemia critically important. Did the sources provide any statistics just to underscore the global impact? Give us a sense of scale.
Yes, actually, one source specifically cites a World Health Organization statistic that really puts the scale of the problem into perspective. It indicates that high blood cholesterol levels alone contribute to approximately 56% of cardiovascular disease cases worldwide.
56%. Wow.
Yeah, and tragically, this contributes to about 4.4 million deaths globally each year.
4.4 million deaths
Yeah.
annually.
Annually. That number really highlights the immense public health burden associated with dyslipidemia or, unhealthy lipid levels.
Wow, that certainly explains the urgent need for effective management strategies, doesn't it? So, based on the sources, then, who are the main players in this lipid landscape that we'll be discussing as we go through these studies?
So the key characters, as they're presented in the sources, are definitely LDL, often called the bad cholesterol. High levels are particularly concerning because they're so strongly associated with that plaque buildup in the arteries we mentioned.
Hmm.
Then there's HDL, the good cholesterol. And for HDL, having low levels is considered a risk factor.
So, you want that one higher.
Ideally, yes. And finally, triglycerides. These are another type of fat found in the blood. High triglyceride levels are also linked to increased risk, especially when they're combined with other factors like obesity or diabetes. And the sources point out that triglyceride levels are particularly influenced by things in our lifestyle, dietary factors, weight, intake of sugar, and also alcohol consumption.
Okay, so the goal in managing hyperlipidemia, as these studies we're looking at are exploring, is generally about lowering that LDL and the triglycerides, maybe potentially raising the HDL, and just addressing that overall imbalance. Now, as you highlighted right up front, we're diving into some studies that might not be, let's say, mainstream knowledge yet. Let's begin our exploration with the findings from animal research. Why do scientists even start there? Why rats and rabbits?
That's a great question. Animal studies, and yes, you often see models like rats or rabbits because they can mimic certain aspects of human conditions in a very controlled way. They're really a foundational step in biomedical research. They allow scientists to conduct investigations into the potential effects of new substances, explore possible mechanisms of action, how something might be working, and also establish preliminary safety profiles. All this happens in a highly controlled environment before they even consider advancing to human trials.
Right, it's like the first testing ground.
Exactly. It's the stage where researchers gather that initial crucial evidence on whether a substance even has potential therapeutic effects worth pursuing further.
And our sources included some truly intriguing findings from these animal models. Let's maybe hone in on one specific compound that really stood out, rutin. First off, what is rutin, and what did this study on it reveal in these hyperlipidemic rats?
Okay, rutin. It's a type of flavonoid. Flavonoids are a large class of plant pigments. You find them in various fruits, vegetables, things like buckwheat, citrus fruits, apples, teas. Quite common, actually.
Oh, interesting.
The study we have on rutin focused specifically on its effects in hyperlipidemic rats. And importantly, these weren't just ordinary rats. Their condition was specifically induced by feeding them a high-fat diet over a period. So they were effectively creating an animal model that simulated aspects of diet-induced hyperlipidemia, something we see commonly in humans.
So they basically created the problem in the rats first, to then see if rutin could help solve it or at least improve it. What was the experimental setup? How did they design this particular study?
It was actually quite a well-structured study. They included several distinct groups to allow for robust comparison. First, there was an induced control group. These rats got the high-fat diet to become hyperlipidemic, but then they were left untreated. This group serves as the baseline, showing the extent of the problem caused by the diet.
Okay, this starting point.
Exactly. Then there were the treatment groups. These rats received the high-fat diet plus rutin, and they tested it at two different dosages. One at 40 milligrams per kilogram of body weight per day, and a higher dose of 80 milligrams per kilogram per day.
Trying different levels.
Right. And finally, there was a positive control or comparison group. These rats received the high-fat diet plus a standard, known lipid-lowering drug given at a dose of 20 milligrams per kilogram per day. This setup allowed the researchers to compare rutin's effects, not just against doing nothing, but also against a benchmark pharmaceutical intervention.
That's a pretty solid design for an animal study, comparing it against both no treatment and a standard treatment. So what were the specific quantifiable results they observed, particularly focusing on that higher 80 millikilogram rutin dose compared to the untreated hyperlipidemic control group? What happened to the lipid levels?
Well, the results for that 80 millikilogram rutin group were reported as quite striking, and the source gave specific findings. Compared to that induced control group, the ones just getting the high-fat diet, these rutin-treated rats showed significant decreases in several key serum lipid markers.
Okay, like what?
Specifically, there were substantial reductions reported in total cholesterol and triglycerides and LDL, that bad cholesterol, and also in VLDL. And interestingly, the study also noted an improvement, meaning an increase in the HDL levels, the good cholesterol, with this higher rutin dose. So it really seemed to show a positive effect across the whole spectrum of lipids they were measuring in the blood.
Wow. Significant reductions in the problematic lipids and an improvement in the beneficial one. That's certainly a broad positive impact seen in this particular animal model. Did this study try to quantify the potential reduction in, say, heart disease risk based on these lipid changes?
Yes, they did, and this is actually a key finding that was highlighted in the source.
Mhm.
The researchers calculated something called the atherogenic index, or AI.
Atherogenic
Right.
index.
The AI is essentially a ratio that's derived from different lipid levels. Often it involves total cholesterol and HDL, or sometimes LDL.
Yep.
It's used by researchers as an indicator, a way to estimate the risk of developing atherosclerosis and the associated cardiovascular diseases.
Okay, so it's like a risk score based on the lipid profile.
Exactly. And the study reported that the 80 millikilogram rutin group showed a percentage protection based on this AI calculation of 55.57%,
55% protection.
which is particularly noteworthy because the standard drug they used in the study for comparison that showed a percentage protection of 60.63%.
Huh. So in this specific rat model, and based on this specific risk index calculation, the higher dose of rutin showed a potential for risk reduction that was numerically, well, pretty close to, or at least comparable with, the standard drug they used. That feels like a powerful finding for a natural compound, doesn't it? Suggests a magnitude of effect worth looking into further.
It certainly does suggest that, yes, a comparable effect size in this model is quite interesting.
Did the sources offer any insight into how rutin might be doing this, beyond just influencing the numbers? Did they look at potential mechanisms?
Yes, another source we looked at, which actually investigated a combinatorial treatment that included rutin, provided some really interesting insights into potential mechanisms. Specifically, it linked rutin to antioxidant activity.
Antioxidant, okay.
This source reported findings that giving rats a high-fat diet led to a decrease in important endogenous antioxidants. These are substances the body naturally produces to combat cellular damage, things like SOD, superoxide dismutase, C-catty T catalase, and GSH, which is reduced glutathione.
So the bad diet depleted the body's own defenses.
It seems so in this model. And at the same time, that high-fat diet increased the markers of oxidative stress. The source mentioned MDA, malondialdehyde, and NO, nitric oxide. Oxidative stress, just to clarify, is essentially cellular damage caused by an imbalance between harmful free radicals and the body's antioxidant defenses. It's heavily implicated in the development of many diseases, including atherosclerosis.
Right, I've heard that term. So the high-fat diet wasn't just messing with the lipid numbers, it was also causing this damaging cellular stress by knocking down the body's defenses and ramping up the damage markers.
Exactly. And the really key finding from this particular source was that the combinatorial treatment, the one that included rutin, was found to significantly restore those depleted antioxidant enzymes. And it also decreased the elevated levels of MDA and NO in the high-fat diet rats.
So it helped reverse that oxidative damage pattern.
It appeared to, yes. And what makes this finding particularly interesting is that the source highlighted that this specific combination demonstrated enhanced antioxidant activity compared to using a higher dose of simvastatin, which is a widely used statin drug alone.
Whoa, hold on. Better antioxidant effect than the statin alone in this model.
That's what this source reported, yes. Enhanced antioxidant activity compared to the higher dose of simvastatin alone in these HFD rats.
That's incredibly insightful. It suggests rutin isn't just, say, tweaking the lipid levels directly, but it might also be tackling one of the underlying damaging processes, that oxidative stress, that's linked both to the high-fat diet and potentially to the progression of atherosclerosis itself. So, okay, let's try to put these findings together, just based on what the sources tell us. We have significant lipid improvements, comparable AI protection in one study, and these robust antioxidant effects shown in the other. What does this combination suggest about rutin's potential mechanisms or maybe its broader benefits, sticking only to the information provided in these sources?
Okay, based strictly on these specific sources, the combination of observing those significant lipid panel improvements and the demonstrated effectiveness in combating oxidative stress markers, all within these rat models, it strongly suggests that rutin might possess a kind of dual mechanism of action.
Dual action.
Potentially, yes. On one hand, it could be influencing lipid metabolism pathways more directly, leading to those observed changes in cholesterol, triglycerides, LDL, and VLDL.
Huh.
But simultaneously, its potent antioxidant activity could be mitigating the cellular damage and the inflammatory stress induced by the high-fat diet, which we know is a contributor to atherosclerosis development. This potential dual action tackling both the lipid imbalance and the associated oxidative damage is a really fascinating possibility highlighted by these animal studies. It suggests maybe a broader therapeutic potential beyond just lowering numbers. Although, of course, and this is crucial, these are animal results, and they absolutely require further human validation.
Absolutely. Animal models are just the start. But that potential dual action certainly makes Rutin's profile particularly interesting to follow. Okay, let's move on to another fascinating compound mentioned in the animal studies, one that sounds, well, even more complex. Oleolethanolamide, OEA. What is this substance and how was it investigated?
Right, OEA. It's described in the sources as a naturally occurring lipid mediator. Now, lipid mediators are basically signaling molecules that are derived from lipids, from fats, and they play roles in all sorts of biological processes, including metabolism. OEA itself is actually found in certain dietary sources, particularly fats.
Found in food, okay.
Yeah.
But how did they study it? Did they feed it to the animals?
Interestingly, no. The study we have didn't investigate dietary intake. Instead, it involved administering OEA directly to the animals via injection, specifically intraperitoneally, which means injecting it into the abdominal cavity.
Why inject it?
Well, that method allows researchers to bypass the complexities of digestion and absorption in the gut. It ensures the compound is delivered systemically throughout the body so they can measure its direct effects without those variables. It gives a clearer picture of the compound's inherent activity.
Makes sense. Isolate the effect. What kind of animal models did they use for this OEA study?
They used multiple animal models, actually, which is good for seeing if the effects are consistent. One model involved obese sucker rats. These rats are genetically predisposed to obesity. They have a defect in their leptin receptors, which makes them a common model for studying certain types of metabolic dysfunction, like insulin resistance.
So a genetic model of obesity.
Yes. And then they also used diet-induced obese rats and mice. In these models, the obesity and the associated metabolic issues, including hyperlipidemia, were brought about simply by feeding the animals a high-fat diet, similar to the Rutin study we just discussed. Using these different models helps researchers confirm if the observed effects are specific to, say, a particular genetic background, or if they are more broadly applicable to obesity caused by diet.
A good approach to see if the findings are robust across different types of obesity models. What was the treatment protocol? How much OEA did they give? And for how long?
The animals received what's called subchronic OEA treatment. That just means it was given consistently over a period rather than just a single shot. The specific regimen reported was 5 milligrams per kilogram of body weight, administered once daily for a duration of 2 weeks.
2 weeks daily. Okay. And what were the key effects they observed in these different animal models after those 2 weeks of OEA treatment?
The study reported several quite notable effects. In the obese sucker rats, the OEA treatment resulted in reduced food intake.
Oh, interesting. Appetite suppression.
It appeared that way, yes. Reduced food intake, which subsequently led to lower body weight gain compared to the untreated controlled Zucker rats. And crucially, for our focus here on lipids, the treatment also significantly decreased plasma lipid levels. Specifically, it lowered both serum cholesterol and triglycerides in these rats.
Okay, lower cholesterol and triglycerides plus effects on appetite and weight gain in that genetic model. What about the diet-induced models?
The sources mention that similar positive effects on food intake, body weight, and those plasma lipids were also observed in the diet-induced obese rats and mice as well.
So it worked similarly in both types of models. That suggests OEA, at least when injected at these doses, was having a kind of multifaceted effect, helping with weight management parameters like reducing food intake and weight gain, but also directly improving key lipid markers like cholesterol and triglycerides. Did the researchers dig any deeper? Did they look at the molecular level to try and understand how OEA might be achieving these effects?
Yes, they did. The study included investigations into OEA's molecular actions, and a key finding was that OEA treatment initiated the transcription, basically, the activation of something called PPAR-alpha and its target genes.
PPAR-alpha sounds important.
It is. PPAR-alpha is a type of nuclear receptor. Think of it like a protein switch inside cells, particularly in tissues involved in metabolism, like the liver, heart, and muscle. It plays a really critical role in regulating the metabolism of fatty acids, how the body breaks down and uses fats.
Okay, so ODA flips this PPAR-alpha switch on.
It appears to initiate as transcription, yes. And the target genes that were activated by this included ones involved in fatty acid transport, and binding the source mentions FATCD36 and LFABP, as well as a gene called UCP2, which is linked to energy expenditure and heat production.
Genes related to moving fats around and maybe burning energy.
Exactly. And furthermore, the study found that OEA treatment decreased the content of neutral lipids within hepatocytes. Hepatocytes are the main type of liver cell. This decrease in liver fat was assessed using specific staining techniques, allowing them to actually visualize the fat accumulation, or lack thereof, in the liver tissue.
Okay, let's try to break that down a bit more simply. So PPA alpha is involved in processing fats. Activating it and activating these genes involved in fatty acid transport suggests OEA is kind of telling the body, maybe specifically the liver and other metabolic tissues, to handle fats differently. Maybe burn them for energy more or transport them more efficiently instead of storing them.
That's a good way to think about it. Activating PPAR alpha is indeed generally a signal to increase fatty acid breakdown or oxidation and potentially energy expenditure.
And what about decreasing the neutral lipids, the fat in the liver cells? What does that imply?
Decreasing neutral lipid content in hepatocytes suggests that OEA is preventing or reducing the accumulation of fat within the liver itself. This is really significant because a condition called non-alcoholic fatty liver disease, or NAFL, which is characterized by fat buildup in the liver, is very often associated with obesity, insulin resistance, and also dyslipidemia, the very lipid problems we're discussing.
Ah, right, fatty liver disease.
So OEA's action on PPAR alpha and the subsequent observation of reduced liver fat points towards a potential mechanism where it actively influences how the body processes and stores fat. It might be diverting fat away from storage in key organs like the liver and promoting its utilization or breakdown instead.
That's a really powerful potential mechanism influencing a fundamental pathway that governs how the body handles fat and potentially reducing fat in a critical organ like the liver. The study also included a comparison to some synthetic compounds, didn't it? What did that show?
Yes, they did include that comparison. The study mentioned that synthetic agonists, man-made molecules designed to activate related receptors, specifically GW50151-sine, which targets a different PPAR called PPAR delta, and siglitazone, which is a synthetic agonist for another one called PPAR gamma. These did not show the same effects on these parameters in their models.
So hitting other related PPAR switches didn't do the same thing as OEA.
Apparently not, according to this source. This finding is important because it suggests that OEA's action isn't just some general effect you get from activating any PPAR receptor. It implies that OEA might be acting via a distinct or perhaps specific pathway that's primarily mediated through PPAR alpha. It offers potentially a unique angle compared to compounds that might target other members of this receptor family.
That distinction really reinforces the idea that OEA has a very specific biological activity through that PPAR alpha route. So stepping back, what's particularly intriguing about finding that a naturally occurring lipid mediator like OEA shows the significant effects on metabolism and lipids when it's administered. Even though, yes, it was via injection and not diet in this specific study, how might this connect back to dietary considerations, if at all, based only on what the source tells us?
What's fascinating, I think, is the very existence of a natural signaling molecule like OEA within our bodies, derived from dietary components, that can exert such potent effects on these core metabolic pathways, food intake, weight gain, plasma lipids, at least in these animal models, when given exogenously. Now, while this study used injection, as we stressed, to isolate the compound's effect, the fact that OEA is found in some dietary fats naturally raises some really intriguing questions, doesn't it?
Yeah,
Like, could dietary intake of OEA itself, or perhaps consuming other dietary substances that might influence the body's own production or breakdown of OEA, have similar, maybe more subtle effects over a longer period? The study doesn't answer that directly, of course, because it didn't test dietary OEA, but it certainly highlights that the body's own complex internal lipid signaling system, which is potentially influenced by our diet, could be a valid target for managing metabolic health. It really points to the sophistication of these natural compounds and how they might interact with our own internal regulatory networks.
it certainly opens up a new avenue of thinking, doesn't it, about how diet and these naturally occurring substances might interact with our internal metabolic machinery in ways we're just starting to understand. Now, beyond rutin and OEA, the sources touched on several other notable findings in various animal studies. Let's maybe just touch on some of those briefly to show the breadth.
Yes, definitely. There were a few other examples cited that really illustrate the breadth of animal research happening in this area. One source mentioned a study conducted on rabbits using an extract from Emblica officinalis. This is commonly known as amla, or Indian gooseberry.
Amla. Okay, I've heard of that.
This study reported that the amla extract significantly reduced serum total cholesterol levels in the rabbits, and importantly, It also seemed to reduce cholesterol accumulation in key tissues, specifically in the aorta, which is the main artery where atherosclerosis develops, and also in the liver. This was seen in both normal rabbits and in those that had induced hypercholesterolemia.
So AMLA showed potential in rabbits for reducing cholesterol not just in the blood, but also preventing its buildup in critical tissues involved in heart disease progression.
Precisely. It suggests a broader potential anti-atherogenic effect, at least hinted at by that study. However, it's worth noting, the study also mentioned it did not appear to significantly affect serum triglyceride levels in this specific rabbit model.
Okay, so primarily cholesterol effects in that one. What else?
Another study site involved the plant Solanum nigrum, which is also known as black nightshade. This particular research was conducted in rats that were specifically intoxicated with ethanol alcohol, creating a model of liver damage that's often associated with lipid dysregulation.
An alcohol-induced damage model.
Yes, and the acrease extract, basically a water-based extract derived from the fruit of Solanum nigrum, was found to significantly improve their lipid profile levels, helping to normalize them. Interestingly, the effects observed were reported as being comparable to silymarin, which is a well-known compound derived from milk thistle, often used for liver protection.
Interesting that they used that specific model of induced damage and found effects comparable to a known protective agent like silymarin.
We also saw some specific data presented in a table within one of the sources. This table compared the effects of proanthocyanidins, often abbreviated as OPC, and pterostilbin, or PT, in rats.
Okay, OPC and PT, what are they?
Proanthocyanidins are a class of polyphenols, antioxidants found in many plants, things like grape seeds, pine bark, cranberries. Pterostilbin is a stilbenoid compound, chemically related to resveratrol, and found in things like blueberries and grapes.
Got it. And what did the table show for their effects in rats?
According to the data presented in that table, the OPC treatment significantly affected multiple lipid parameters in the rats. This included total cholesterol, triglycerides, LDL, and VLDL, all showing significant improvement. It also showed a significant improvement in that atherogenic index we discussed earlier.
So broad effects for OPC. What about pterostilbin?
Pterostilbin, or PT, also significantly affected total cholesterol, triglycerides, LDL, and VLDL, according to the table, and it also improved the atherogenic index. The table did note statistical significance for both compounds across most parameters measured, although, maybe a fine point, for LDL and VLDL, the reported p-values for pterostilbin seem to indicate a slightly weaker level of statistical significance compared to the results for OPC or for other parameters for PT itself, which were often highly significant.
Okay, so maybe subtle differences in the statistical strength, but overall, both OPC and pterostilbin showed broad positive impacts on the lipid profiles and that risk index in these rat studies based on that specific data table.
Correct. The table provided clear quantitative results supporting those findings for both compounds in that model. And finally, just to round out the animal findings, there were also brief mentions in the sources of investigations into other plants. One source cited studies indicating hypolipidemic or anti-atherogenic effects of Ficus glumosa extract in rats.
Ficus glumosa, okay.
And another source mentioned studies showing antioxidant and anti-hyperlipidemic effects of Todalia asiatica leaves, also in rats. These just serve as further examples highlighting the vast diversity of the plant kingdom and how researchers are really casting a wide net, exploring substances from many different species for their potential effects on lipids and other heart health markers, at least in these initial animal models.
It really does underscore just how much potential is being investigated out there in nature from all these different sources. But as we established earlier, while these animal studies provide absolutely crucial insights into potential efficacy and maybe how things work, the real question always comes down to, do these findings actually translate to humans? What happens when these substances are tested in people?
Exactly. That's the critical next step. Human clinical trials are necessary to confirm if the potential benefits seen in animals are actually replicated in the target population, humans. They're needed to determine safe and effective dosages for people and to assess the overall safety profile in a real-world context. Human trials are essential for validating the earlier findings and potentially moving the research towards practical applications.
So let's shift our focus now squarely onto the studies conducted directly in human subjects that were highlighted in our sources. And one ingredient in particular presented some, well, quite remarkable, even dramatic results. Monascus purpureus went rice. Most people probably know this better as red yeast rice.
Yes, red yeast rice. This was a human efficacy and safety trial described in one source. It was designed as a randomized study, which is important for quality, and involves 75 participants who successfully completed the entire trial. Randomized trials, as you know, help minimize bias and really increase our confidence that the effects we see are actually due to the intervention itself and not just some other factor.
Right, the gold standard design. What was the main outcome the researchers were really trying to measure in this particular study? What was their primary efficacy endpoint?
Their primary efficacy endpoint was the change in LDL-C levels. LDL cholesterol is such a key target in lipid management, mainly because of its strong link to atherosclerosis and heart disease risk.
Makes sense to focus there. And what were the results for LDL-C in the group that received the Monascus purpureus went rice? You said they were dramatic.
They were indeed reported as quite dramatic. By week 8 of the study, the group getting the red yeast rice showed a remarkable 27.7% reduction in their LDL-C levels compared to the placebo group. And the placebo group saw only a minimal change, about a 1.5% decrease.
Wait, nearly 28% reduction in LDL-C in just 8 weeks?
Yeah.
That is a very significant drop. That's the kind of magnitude you often hear associated with standard pharmaceutical lipid-lowering interventions like statins. That seems like an extraordinary finding for a natural product.
It is a substantial reduction reported in this trial, yes.
Were there effects on other lipids as well, besides LDL?
Yes, the study reported further significant reductions in other key lipid parameters at that same 8-week mark. Total cholesterol levels in the Monascus purpureus went rice group decreased by 21.5%, triglycerides were reduced by 15.8%, and apolipoprotein B, ApoB, which is a major protein component of LDL and VLDL, and is also considered a very strong marker for cardiovascular risk, showed a significant reduction of 26%.
Wow, so it wasn't just LDL, it was a broad positive impact across multiple important markers of dyslipidemia, total cholesterol, triglycerides, ApoB, all significantly down. Did these effects take a long time to show up, or were they relatively quick?
That's another notable finding the study specifically highlighted, the speed of the effects. They observed significant reductions in these key lipid parameters remarkably as early as 4 weeks into the study.
4 weeks. What were the numbers then?
At week 4, the reduction in LDL-C was already measured at 30.6%. Total cholesterol was down 23.7%. Triglycerides saw a 13.4% decrease, and apolipoprotein B was reduced by 28.9%.
Even faster results at the earlier measurement point, a 30% drop in LDL in just 1 month. That speed and magnitude of effect are truly impressive. It really stands out from many other natural interventions where effects might take longer to appear or perhaps be more modest in size. Did it affect all the lipids they tracked, though? What about the good cholesterol, HDL?
That's a good question. The study did note that the Monascus purpureus went rice had a limited capacity to change HDL-C levels and also apolipoprotein AI levels. ApoAI is the major protein component of HDL. The changes they observed for HDL and ApoA are not statistically significant and were comparable to the very small changes seen in the placebo group.
Okay, so its power, demonstrated in this study at least, was primarily on reducing the bad lipids and related markers, LDL, total cholesterol, triglycerides, and ApoB, and doing so rapidly and significantly, but not so much on boosting the good HDL.
That seems to be the primary strength highlighted by this particular human trial, yes. That powerful effect on reducing multiple key risk factors is certainly a major takeaway.
Absolutely. It's a finding from the sources that definitely warrants attention due to that magnitude and the speed of the lipid reductions observed.
Okay, another promising natural source investigated in human studies that our sources touch upon is krill oil.
Ah, yes, krill oil. It has gained quite a bit of popularity recently, often positioned as an alternative to standard fish oil.
Exactly. So what did this study on krill oil in our sources find regarding lipid management in humans? This was described as a multi-center human study, meaning it was conducted at several different locations, which can potentially add to the generalizability of the findings. It suggests the results aren't just specific to one clinic or population. It was a 3-month prospective randomized trial, and it involved 120 patients who already had diagnosed hyperlipidemia.
120 patients over 3 months? How was the study designed? What were they comparing?
They compared 3 distinct groups. There was a group receiving krill oil. Interestingly, the dosage for krill oil was adjusted based on the patient's body mass index, their BMI, so it ranged from 1 gram up to 3 grams per day.
Personalized dosing based on size. Okay.
Seemingly so. Then there was also a group receiving standard fish oil at a fixed dose of 3 grams per day. And finally, there was a placebo group receiving an inert substance. This design allowed for a direct comparison of krill oil against both a common alternative, fish oil, and against a placebo.
Good comparison groups.
Yeah.
And what was the conclusive finding from this 3-month trial? What did krill oil do?
The main conclusion presented in the source was that krill oil, administered at that dosage of 1 to 3 grams per day, was found to be effective for improving several important metabolic parameters. This include the reduction of glucose levels.
Glucose too. Interesting.
Yes, glucose levels, total cholesterol, triglycerides, and LDL cholesterol. But notably, the study also found that krill oil increased HDL cholesterol levels, the good kind. And importantly, this effectiveness across this range of markers, glucose, TC, TG, LDL reduction, HDL increase, was demonstrated when compared to both the fish oil group and the placebo group in this study. The source specifically highlighted that in this trial, krill oil showed broader positive effects than the fish oil did.
Wow, okay. That's a very significant finding. Not only did krill oil seem to reduce the problematic lipids and even glucose, but it also managed to increase the beneficial HDL cholesterol. And it did so, according to this study, more effectively, or at least across a wider range of markers than the standard fish oil they use for comparison. Now, based only on the source text, did it give any hints as to why? What might be a potential reason suggested for krill oil's potentially broader effects compared to fish oil in this instance?
The source itself doesn't actually provide a detailed mechanistic explanation for why krill oil might have had these broader effects than standard fish oil in this specific trial. However, if we think about it, krill oil is known to be a complex marine lipid source. It contains not just the omega-3 fatty acids, EPA, and DHA that you also find in fish oil, but it also contains other compounds like phospholipids, which might affect absorption, and the antioxidant astaxanthin.
Right, it's structured differently.
It is. And if we recall our earlier discussion about OEA being a naturally occurring lipid mediator that influences metabolic pathways, well, one could speculate, and this is purely speculation based on putting pieces from the sources together, that perhaps the unique composition of krill oil, maybe those phospholipids or other minor components, might contribute to these more comprehensive effects observed on glucose, cholesterol, triglycerides, LDL, and HDL, going beyond just the effects of the omega-3s typically found in standard fish oil. But again, to be very clear, the study text itself simply presents the observed outcome, that krill oil showed broader effects in this trial. It doesn't confirm the reason why.
That's fair. We have to stick strictly to what the sources say. But
Yeah.
it definitely prompts some fascinating questions about the nuances between different natural lipid sources, doesn't it? Okay, let's turn now to Dongtongxia cow, which many people know as cordyceps, the caterpillar fungus. Our sources included some human study findings for this one too, but they seem to present a bit of a mixed picture, particularly when it comes to triglycerides.
Yes, that's right. The findings reported for cordyceps in patients with hyperlipidemia, as they were cited from different studies mentioned in our sources, do show some variability, which is definitely important to note.
Okay, so what did the first study mention about cordyceps find?
One study described involved 273 patients who had hyperlipidemia. It reported that giving them 1 gram of Dongtongxia cow 3 times a day showed a marked action to decrease both LDL cholesterol and triglycerides. Furthermore, this particular study indicated that it also had an action to increase HDL levels. So based on that study, it suggested a positive effect across LDL, triglycerides, and HDL.
Okay, so that sounds like a generally beneficial profile reported in that specific trial. Lower bad stuff, lower triglycerides, higher good stuff. Now, what did the second human study that was mentioned for cordyceps report?
The second study involved 204 patients. Now, in contrast to the first study's finding on triglycerides, this study reported that cordyceps administration decreased LDL levels, similar to the first study, but it actually increased triglyceride levels.
Oh, okay, there's the inconsistency you mentioned. So both studies apparently saw a decrease in LDL, the bad cholesterol, but they reported completely opposite effects on triglycerides. One found a decrease, the other found an increase. What could this kind of variability between different studies suggest when we're researching complex natural compounds like this?
That's a really important point. This kind of inconsistency, particularly in something like the triglyceride result here, it's actually not that uncommon when you're looking at research on complex natural substances. It can suggest several possibilities just based on general scientific principles.
Like what?
Well, it might be due to differences in the patient populations that were studied. Perhaps there were variations in age, baseline diet, genetic factors, or maybe other underlying health conditions between the groups in the two studies that influenced how they responded. Differences in the specific preparation or strain or even the dosage of the cordyceps used could also play a significant role because, as we know, natural products can vary quite a bit in their exact chemical composition.
Right, not all cordyceps is necessarily the same.
Exactly. Furthermore, differences in the study design itself, Maybe the duration of the study or even how the triglyceride levels were measured and analyzed could contribute to the discrepancy. It really highlights the inherent complexity of working with natural compounds and underscores the importance of replication, doing more studies, and also standardization in research to try and understand when and why results might vary like this. It tells us the picture isn't always simple or universally consistent across different studies for these types of interventions.
That makes a lot of sense and is a really valuable point about interpreting research findings, especially with natural products. Okay, now let's talk about something that might feel a bit more familiar to many listeners: plant sterols and stanols. These seem to pop up more often, especially as additions to certain foods.
Yes, plant sterols and stanols are compounds that are structurally very similar to cholesterol itself. They occur naturally, although usually in small amounts. In various plant-based foods, you find them in fruits, vegetables, nuts, seeds, legumes, vegetable oils. And as you said, they're also often added to certain fortified food products, things like some margarine, certain yogurts, sometimes orange juice, and even milk. They're added specifically because of their known cholesterol-lowering properties.
And how do these compounds actually work to lower cholesterol? What's the mechanism described in our sources?
Their mechanism of action is actually quite well defined and was described clearly in the sources. When you consume them, either naturally in foods or from fortified products, plant sterols and stanols basically compete with dietary cholesterol for absorption in your gut.
They compete. How?
They essentially get in the way. They block some of the cholesterol that you eat, and also cholesterol that comes from bile, from being absorbed from your digestive tract into your bloodstream. Because they look similar to cholesterol, they kind of take up the absorption spots.
Ah, okay. So it's a direct physical blocking action right there in the digestive system, preventing some of the cholesterol you consume or that your body recirculates from ever actually getting into your system properly.
Exactly. It reduces the total amount absorbed. And the scientific evidence that was cited in the sources supporting their efficacy is actually quite strong. Taking about 2 grams of plant sterols or stanols daily has been consistently shown to reduce LDL cholesterol levels by a significant amount. The sources typically state a range of about 6% to 15%.
6 to 15% LDL reduction from 2 grams a day. That's quite specific.
Yes. And the sources note that this effect seems to be particularly pronounced when these compounds are incorporated into a diet that is also low in saturated fat. So combining approaches helps. Importantly, they were described as primarily affecting LDL cholesterol. They generally lower LDL without significantly changing HDL cholesterol or triglyceride levels. So it's a targeted LDL lowering effect.
A very targeted mechanism blocking absorption, leading to a specific reduction in LDL, especially when combined with other healthy dietary changes. Did the sources offer any practical advice on how someone might actually incorporate that 2 grams per day target into their diet?
Yes, one source did offer a specific dietary recommendation, more as an example of how you could achieve that target intake. It suggested aiming for about 2 to 3 servings of milk that has been fortified with plant sterols as one potential way to get the approximately 2 grams per day needed for that effect. This just shows how researchers and health bodies are thinking about translating these findings into practical, actionable dietary advice for people.
That's definitely helpful for connecting the dots between the research finding and potential real-world application. Okay, so besides those quite detailed studies on red yeast rice, krill oil, and the more familiar plant sterols, what other human findings were mentioned in the sources? Perhaps with less detail provided, but still noteworthy results on other substances.
Yes, there were mentions of several other substances being investigated in humans as well. One source discussed findings related to Gynostema pentaphyllum. This is also known as Jiogulan, or sometimes called southern ginseng.
Gynostema, okay.
In the context of a meta-analysis, which, remember, is a study that statistically combines the results from multiple previous studies, Gynostema showed an ability to increase HDL cholesterol levels, the good cholesterol. The source reported this finding with statistical significance, providing the quantitative measures like the standardized mean difference, SMD, and the confidence interval, Phi, to back it up.
So an increase in HDL shown in a meta-analysis. That sounds positive.
It does, but, and this is crucial, the source also took care to highlight that there was significant heterogeneity observed among the individual studies that were included in that meta-analysis.
Heterogeneity, meaning the results of the individual studies varied quite a bit.
Exactly. So while the overall combined result pointed towards a benefit for HDL, the fact that there was significant heterogeneity means the individual studies that contributed to that overall finding likely varied considerably in their results, or perhaps their methods, or the populations they studied. It's similar to the point we made about the cordyceps variability. It means you have to interpret that overall meta-analysis result with some caution, acknowledging the underlying inconsistency among the studies that pooled together.
Got it. Important caveat there. What else? You mentioned AMLA earlier in rabbits. Was there a human follow-up mentioned?
Yes, there was. Following up on that rabbit study, a source also noted a human study conducted on Emblica officinalis, EMBLA. This trial involved individuals who had hypercholesterolemia, aged between 35 and 55 years old. They were given the raw form of AMLA for 28 days. And the study reported that this intervention reduced their total serum cholesterol and also its lipoprotein fractions, which implies it positively impacted LDL and potentially other related lipid components in these human subjects.
Interesting. So the cholesterol-lowering potential seen in the rabbit study for AMLA seemed to translate, at least to some extent, to effects in humans in this particular trial.
It appears so, based on that report. There was also a note on Terminalia arjuna. This is a medicinal plant often used in traditional Ayurvedic medicine. The source mentioned a finding that an alcoholic decoction, basically, a concentrated liquid extract made using alcohol prepared from the bark powder of Terminalia arjuna, was found to lower serum cholesterol levels in patients who already had diagnosed ischemic heart disease.
So showing effects in a relevant patient population, people with existing heart conditions, that's notable.
It is. And connecting back to the animal findings we discussed earlier for Astragalus membranaceus, also known as Huangqi, animal studies had suggested effects on lipid metabolism. The source mentioned a human finding related to this, specifically noting that polysaccharides extracted from Astragalus were found to decrease lipid deposition, that's fat buildup in the liver, in subjects who were diagnosed with hyperlipidemia.
So that's a direct link between a finding suggested by animal research direction, lipid effects, and a specific human finding showing reduced fat accumulation in a key organ, the liver, in people with the condition.
Exactly. A nice example of potential translation there. Finally, a couple of widely recognized herbs, fenugreek and ginger, were also referenced briefly in the sources. They were mentioned in the context of clinical or human studies having shown hypolipidemic effects or positive effects on lipid levels. However, it's important to note that for these specific human findings on fenugreek and ginger, the sources we had didn't provide detailed quantitative results or descriptions of the studies themselves, just the general acknowledgement that such human trials exist and have reported relevant effects on lipids.
Okay, so the sources confirm that research exists for fenugreek and ginger showing effects in humans, but without the specific data points or study details we saw for, say, red yeast rice or krill oil in these particular documents. Fair enough. There was one final human study mentioned, I think, on the medicinal mushroom Ganoderma lucidum, which is commonly known as lingzi or reishi. What did that specific study find?
Right. The Ganoderma lucidum study, this one was conducted in a specific population. They recruited healthy adults. It involved 18 participants, and the intervention lasted for 4 weeks. Now, the key finding from this particular study, as it was reported in the source, was that while the researchers observed a slight trend towards lowered lipid levels in the group taking the Lingzi supplement, there was no statistically significant change found for the major coronary heart disease, CHD, risk biomarkers over the course of this 4-week study.
Okay, so in healthy individuals, this relatively short trial didn't show a statistically significant impact on the standard markers of heart disease risk, like cholesterol levels.
Correct. The results for efficacy in this specific study design, population, and duration were not statistically significant. However, and this is important, the study did provide valuable safety data. It reported a positive safety profile. They found no evidence of liver toxicity, no renal or kidney toxicity, and no DNA toxicity associated with the Ganoderma lucidum supplementation in this particular trial.
That's interesting. So even though it didn't demonstrate significant efficacy for lipid lowering in healthy adults under these specific conditions, the research still provided important information about its safety profile, at least in that context.
Exactly. That safety finding is valuable context in itself, especially when we're discussing natural compounds. It shows that even if a substance doesn't show strong efficacy in one particular trial design or population group, the research can still contribute important information regarding its safety.
Absolutely. So, okay, we've covered a lot of ground here. Looking across all these different studies and the diverse natural substances discussed in the sources from specific compounds like rutin and OEA in animal models, all the way to extracts and complex preparations like red yeast rice and krill oil in humans, What are the big picture takeaways? How can we synthesize all this information?
Yeah, synthesizing the information from this wide range of sources, I think one of the most striking points is simply the sheer diversity in the types of natural interventions that are being actively explored for lipid management. We've seen research on specific, often isolated chemical compounds like rutin, oleolethanamide, OEA, paranthocyanidins, OPC, and pterostilbin, PT.
Right, the single molecules.
Then there are studies on more complex extracts derived from various plants like Solanum nigrum, Emlica officinalis, Amla, Terminalia arjuna, Ficus glumosa, and Tidalia asiatica. We also looked at research into even more complex preparations like red yeast rice and cordyceps. And we can't forget common food components or fortified foods like mung bean seed coat, which was implied in some traditional uses mentioned, plant sterols and stanols, and the marine source, krill oil. It really demonstrates that researchers are casting a very wide net, investigating many different types of natural substances from diverse origins.
It's definitely not a narrow field, and the potential mechanisms suggested by these studies, even though, as you said, they weren't always fully detailed in the sources we reviewed, they also seem quite varied, don't they?
They really do appear to work through a variety of different pathways. We saw evidence suggesting mechanisms like physically blocking cholesterol absorption right there in the gut, as seems to be the case with plant sterols. There were strong indications of antioxidant effects being important, particularly with rutin, and in that combinatorial study, potentially mitigating the oxidative stress linked to high fat intake and atherosclerosis.
The dual action idea for rutin.
Right. Then OEA seem to be influencing key internal lipid mediator systems and gene transcription related to fat metabolism and storage, specifically activating PPAR alpha. Other substances appear to have more direct effects on lipid synthesis or breakdown or clearance from the blood, although the precise molecular steps weren't always fully elucidated in these particular source summaries we had. It really feels like nature offers multiple different angles of attack on the complex problem of dyslipidemia.
And the strength and type of evidence presented also varied quite a bit across the sources we looked at, didn't it? It wasn't all the same level.
Absolutely not. The sources presented findings that ranged quite widely. We saw general mentions of traditional uses and observed effects in some review articles. Then we had specific, detailed, and often quantitative results obtained from controlled studies in animal models, which allow for those preliminary mechanistic insights. And finally, we saw results from randomized controlled trials in human subjects, providing actual clinical efficacy and sometimes safety data. Studies like those on red yeast rice and krill oil, the rutin work in animals, and that OPCPT data table provided more granular, quantifiable results that give us a clear picture of the magnitude of effects seen in those specific research settings.
And as we noted along the way, particularly with things like cordyceps and maybe the gynostemma meta-analysis, the findings aren't always perfectly consistent across different studies. It highlights the complexity involved.
Yes, acknowledging findings that show complexity or inconsistency is really important for a balanced view. The different reported effects of cordyceps on triglycerides in those separate human studies, and the noted significant heterogeneity in the meta-analysis of gynostemma pentaphyllum studies. These examples underscore the real challenges inherent in studying natural products. As we discussed, factors such as variations in the source material itself, different preparation methods, the dosage used, the duration of the study, the specific characteristics of the participants, and even the study design details can all contribute to differences in outcomes between trials. It just reinforces the fundamental scientific principle that results need replication, and that understanding the reasons for variability is actually part of building robust knowledge in any field, especially this one.
That's a great point. It's not about finding the one answer immediately, but understanding the whole picture, including the variations. Finally, what about safety considerations? The sources touched on this, especially when discussing medicinal plants and traditional Chinese herbs more broadly.
Yes, safety is obviously a crucial aspect whenever we talk about interventions, natural or otherwise. While many natural substances and traditional herbal remedies are often used based on a long history of use, and sometimes perception of being milder compared to pharmaceuticals, the sources do provide important context regarding potential risks. They mention that while these natural products might often be considered less likely to cause severe chronic damage with long-term use compared to certain conventional drugs, potential side effects and interactions are absolutely real possibilities.
Interactions. Like what?
These can include interactions between the herb and prescription medication someone might already be taking. Those are called herb-drug interactions. But there can also be interactions between different herbs or natural supplements if they're taken concurrently, herb interactions.
So just because something is labeled natural doesn't automatically mean it's completely free from potential interactions, particularly if you're taking other medications.
Exactly. That potential for interaction is a recognized concern highlighted in the sources. Hepatotoxicity, which means damage to the liver, is also specifically mentioned as a known, although sometimes idiosyncratic, risk associated with the use of some herbs. Idiosyncratic basically means it's often unpredictable, doesn't necessarily happen to everyone, and isn't always tied directly to the dose in a simple, straightforward way. It can be more of an individual reaction.
That awareness of potential liver issues, even if rare or unpredictable, seems key for anyone considering these options, or for practitioners advising on them.
It really is. And one source specifically suggested that awareness of these potential risks is important for practitioners. It recommended, where possible, avoiding the concomitant use, which just means using multiple herbs or multiple natural substances all at the same time as a strategy to potentially reduce the risk of complex or unpredictable interactions.
Kind of a keep it simple approach to minimize unknowns.
Perhaps, yes. However, it's also worth recalling that positive safety finding from the specific Ganoderma lucidum study in healthy adults we discussed earlier. That trial reported no evidence of liver, renal, or DNA toxicity in that particular setting. So specific studies can provide reassurance for specific products under specific conditions.
Right. So the overall message from the sources regarding safety seems to be a bit nuanced. Potential benefits are being actively investigated across a really wide range of natural compounds, working through various mechanisms. And while many may indeed have good safety profiles based on long traditional use or specific modern studies, a general caution regarding potential interactions with drugs or other herbs, and potential risks like rare hepatotoxicity, particularly when combining multiple substances, is definitely warranted.
Precisely. That captures the nuance well. It's a complex picture that really reflects the ongoing process of scientific investigation into these often quite complex natural interventions.
Wow, that was a truly comprehensive exploration. We've really taken a deep dive into this stack of cutting-edge studies today. We moved all the way from those early animal models, giving us intriguing clues about specific compounds, like rutin's potential antioxidant and lipid effects, and OEA's influence on fundamental fat metabolism pathways, all the way through to human trials, showing some really quite dramatic results for preparations like red yeast rice and broader metabolic impacts from sources like krill oil, alongside important findings on things like plant sterols and various other plant extracts.
And we deliberately focused this deep dive on these specific study findings, the ones highlighted in the sources, to try and provide you with a glimpse into the active scientific investigation that's happening right now at the frontier of natural compound research for lipid management. We wanted to move beyond just the general advice or maybe the most commonly marketed supplements that you might encounter every day and show you what the actual research is uncovering.
It's abundantly clear from our discussion that the research in this field is incredibly dynamic and very much ongoing. As we've seen throughout, the results can vary quite a bit depending on the specific substance being tested, the design of the study, the population involved, and even the exact preparation or standardization of the product used. There's still, clearly, a vast amount to learn and to confirm through further rigorous research.
Indeed there is, and as science continues on this fascinating journey, delving ever deeper into the incredibly diverse array of compounds found throughout nature, it really leaves us with a compelling question to consider as we wrap up today's exploration.
Okay, what's the thought for today?
As we learn more, what unexpected new avenues might continue to open up for managing common yet complex health challenges like hyperlipidemia? And perhaps just as importantly, how will these emerging findings, derived from investigating natural substances, ultimately integrate with, or perhaps even challenge, our current conventional understanding of health, disease management, and treatment strategies?
Very thought-provoking question, for sure, as the research continues to unfold day by day. Well, thank you for joining us on this deep dive into the intricate world of natural compounds and lipid management research.